All right, so I'm going to try and go quickly through this first page because you basically already know everything here. The only thing is like you really have to deal with is the fact that when somebody writes a vector in matrix algebra, it's going to be written in a column instead of kind of like a row. So you're used to a vector, like let's say you have a vector that is, oh, that's too light. So let's say you have a vector that is like 2, -3. And you guys all know that that means you go 2 to the right, down 3, and you have, you know, that vector right there, right? So in matrix algebra, that vector gets written like this. So that's just, it gets written as like a column, right? Okay, so that's that. So basically you're going to see vectors like this. If you want to multiply it by -3, then multiply these numbers by -3, these numbers, and get, let's see, -3, -12, and that would be your answer, right? If you want to do double U, so then it's 4 and -14, okay? All right, but it's in columns. And if you want to do this, you know, you're going to do basically 2, you're going to put your U, plus -3 multiplied by V. And so by the time you're done, you're like, okay, that's 4 plus -3. And that's -14 plus -12, so -26. Okay, so you already like know that stuff. You also know that when you add two vectors, you get the resultant. So you do one action, you tack on another action, you get the resultant, and things like that. Okay, so basically, this is, you know, with all zeros, it's called the zero vector. Yeah, so you know all this stuff right here, okay? You pretty much also know everything on the next page, but let's just look at it real quick. So, oh, there's a zero vector. So it has a bunch of zeros. It's called the zero vector. Okay, and you know, you use whatever size you need. If you have a two-dimensional space, then you're using 2 numbers, 3-dimensional, 3 numbers, and this gets a little bit hard to think of it geometrically here. But remember with vectors, these are all the rules that are okay. You can add vectors in either way you want. You can multiply by a scalar after you add, or multiply each one then add. So these are all just the rules that kind of like we already kind of know. I mean, obviously, if you add a vector and its opposite, you end up getting 0 eventually. So you don't really have to like memorize those rules or write them down. They just like happen naturally, right? So when you do a linear combination of a vector, that's like what we did on this page here. Like this is like a linear combination of a vector. You're like multiplying it and adding with another one. So that would be like a linear combination of a vector, and that's what this is kind of explaining right here. Okay, so we are going to do this one down here and figure out, we have our 2 vectors, this one in red, so this is the red one, this is vector 1. So notice these lines here have been changed, right? So over 2, up 1, so these lines represent all these V1s, and so basically if you want to do 2 V1s, you can kind of see like, oh, right here, that would be 2 V1s, right? Because it'd be 4, 2. So over 4, up 2. So you can like change your space to like, so the lines are not like, you know, perpendicular anymore, like that we normally see, but you change your lines to be the vectors that you're using. And so, you know, if you want, let's say I want 2 V1s plus 3 V2s. All right, so my V2s are these pink ones here. So V2 is backing up. So if I want to do 2 V1s, that puts me 2 this way, and V2s go that way. So if I want 3 of them, 1, 2, 3, I could get there, and it's just like easier because it like the jumps are already marked off for you. So anyway, that would be my resultant, like right here. Okay, so we're going to try to come up with what was done to get to this place, and we're going to use our graph to do it. So 0, 3. So 0, 3 is right here. Okay, so look, to get there, I could do a V1 and add a V2. So letter A can be V1 plus V2, and using my kind of map here to do it. And look, if I add these together, that's what I get. All right, so let's do B. B is at -4, 1. So -4 and 1 would be like here. So that's going to be a little bit harder. But let's see. So, let's try to look at the numbers instead, because I don't really see it happening for me Oh, -4, +1. Oh, that makes a big difference because I'm silly. So -4, 1, oh, so there it is right there. All right, so let's do it. We could take a V2, and this is backwards V1. So I could do V2 plus -V1 or minus V1. I could do this. I could do -V1 plus V2. But, I mean, duh, like you kind of knew that already, all right? Or you could say V2 minus V1, that's fine. But let's take a look. If you take -2 and take away 2, there you go. 2 minus 1 is 1, okay? So you can figure it out with the numbers, or you can use the picture over here. So let's see, 6, 6. So 6 here, 6 there. So here I am. So I could do 1, 2, 3, 4 V1s. All right, and then add a V2. So 4 V1 and add a V2, okay? And you can also just kind of figure it out with just the numbers. So let's just try to take these numbers. If I want 7 and -4, so if I want 7, how about, let's see, how about if I multiplied, so if I want 7, and these are both even numbers, those, I think I picked kind of a hard one to do there. So it might be like a little bit of a half situation. Yeah, I kind of did pick one that's a little bit hard. But what I was trying to say is this, is that you could also like kind of look at the numbers, like let's do 6, 6. If I did like 4 of these, that would get me 8, and I added a -2, like, oh yeah, that's getting me 6. So if I do 4 of these, which gets me 4, and I add 1 of those, it gets me 6. And so you can kind of like play with the numbers if you don't have this picture as well. But this one was actually a little bit too hard to play with the numbers. So let's see. So I got 7, -4. So over to 7, down to -4. So we're kind of like, right, kind of in the middle, right? So to get over there, I think, let's see. So, oh, I kind of put it in the wrong place. So it is like, right, if I like kind of like look over, it is right here on this line. All right, so that's helpful because like halfway. All right, so let's do a V1 plus, let's see, if I went to this line and then went down 1, 2.5, so 2.5 of V2, but V2 is supposed to go this way, so since I'm going backwards, instead of plus, I'm going to say minus. All right, so let's try it out. So V1, so 2, and then 2.5 times this would be, a -2.5 times that would be 5, so 2 plus 5 is 7. All right, and then 1, so 1, and then -2.5 times 2 would be -5, so 1 minus 5 is -4. Okay, so that's just showing you how that picture works a little bit. All right, so let's see. Now to stuff that you might not know, but it's also kind of simple. All right, so when you have a system of equations and you want to write it in vector form, your x1s go in a vector, right? So what we have here, I can tell that -2 is being multiplied by x1, 8 is by x2, all right, and then 1 by x3, and then equals 0. So that's the equation that came from the top times all my variables here. And then the bottom one, I have 3x1 plus 5x2 minus 6x3 equals 0. So this is just the vector form of that system of equations. Okay, so if I want to write a vector equation for this, I take everything and I have 4, 1, 8. So those are my x1s. And I mean, I tend to write it like behind it. It doesn't really matter. And then I have all my x2s, and then I have all my x3s. I don't know, I just feel like it's more natural that way, but it doesn't really matter. And then over here I have 9, 2, and 15. Okay, so the second column, so basically your columns, 1, -7, 6, and 3, -2, 5. So that's just, this is the vector form of that system of equations. So that's it. Okay, so basically what you're going to do is your vector form, if somebody gives you a vector form, you know that it comes from this. And so then you also know that you can write it like we've always been writing it. You can write it as a matrix. You can put your, your equations here. You can augment it with your 9, 2, and 15. Because once we know that this is this, and we know that that's that, so I can just do these, okay? So here's the next important word, this linear combination. So linear combination, we're trying to see if you can multiply these columns and add them together to get this answer. So basically you're trying to see if you can take 1 and multiply it by something, add it with 0 times the next thing, and add it with 2 times the next thing, and get -5. So like we're basically making an equation out of this. You're trying to see if B is possible, if it's possible to use these 3 things to get these things over here. And so you see I just start having a system of equations. So really what I have is a matrix of 1, 0, 2, and -5. All right, I have -2, 5, 0, and 11. I have 2, 5, 8, and -7. Okay, all right, so when you row reduce that, we've done that a lot in class, but when you row reduce it, this 1, 0, 2, -5 stays. But if you just do a couple steps, like you add them together, this goes away, you end up getting this. You get 0, 5, 4, and 1. And the next row also turns into 0, 5, 4, but the last number is a 2. So this mismatch right here, that's like having parallel lines, right? I could use the 5 and the 4 here to get rid of this 5 and 4, subtracting it, but these would not match. So this would not turn into 0. So eventually these would wipe out, but this number here would not wipe out. This would be some kind of number left over, and so I'd have an inconsistent system. So my answer to this question is no. There is no way that you can add and subtract and multiply by a constant with these to get that. Okay. All right, so same question here, but different form. Is this a linear combination of these vectors right here? So it's just put into in a different way. So basically, this is your augmentation right here. You take 1, -2, -6, 0, 3, 7, 1, -2, 5, 11, -5, 9. All right, you can pop that in your calculator, but if you do, let's see what you get. Oh, let's see, 3 by 4, yes, all right. So I got 1, -2, -6, 11, 0, 3, 7, -5, 1, -2, 5, and 9. All right, and then let's RF that. Okay, and if you want to make it a fraction, you can. So they're nice little answers, but yes. So look, this is a solution. It has a definite solution. And so my question, determine if it's a linear combination, I would say yes, because there is a solution. So you can get this thing here by multiplying and adding these columns, by linear combinations of these columns. Okay, all right. So a little definition here, span. So the span of a set of vectors is all the possible linear combinations of that vector. So you would also say here, this is definition down below, you would say that B is in the span of the vectors in A. So to be in someone's span means that you are a linear combination of the things in that matrix or those vectors. Okay, so these are 2 big words: linear combination, span. Like you see those like quite a lot. Okay, so to be in the span means that you could take the vectors given to you and you could add and multiply them by a constant and add them together, subtract them, whatever. You can do something to these vectors to get this one right here. Okay, and the full span is all the linear combinations of those vectors. Okay, so let's get to this last little bit here. I'm going to try and squeeze it in here. All right, so the geometric definition of span. So go ahead and read through that, but let's just read this down here. If U and V are non-zero vectors in 3 dimensions. All right, with v is not a multiple of u. So up here, these vectors are multiples of each other. So like they're always going to follow like the same little line right here. But you see this orange and this pink one here, or whatever colors they are, they're not in the same thing. Like one points that way, one points that way. So they're not multiples of each other. Okay, so that's what it's talking about. Then the span of u and v together is the plane that's produced. So do you see this plane here? These are all the additions and subtractions and multiplied by a constant that these produce. So like let's call this one u and this one v. If I wanted 2u plus v, look, I go 2 of these plus that. So it's on that plane. So the span of all the linear combinations of these 2 vectors produces like a plane, like a surface of all the places that you could end up if you did a linear combination of these vectors. So that's all it is. Okay. All right. So we have our vector 1, vector 2, and y. It says for what values of h, so notice h there, is y in the plane generated by v1 and v2. So they're basically asking you this. When is this in the span of these vectors? So you know what we do? We take these 2 vectors, and the sky is our augmentation. So 1, 0, negative 2, negative 3, 1, 8, and h, negative 5, negative 3. Now, I can't put this in my calculator because of that h right there, but I'm going to do a couple row operations. I'm going to do 2 times row 1 and add it to row 3. And let's see what we get. So when I do that, I get 1, negative 3, and h. This is not changing. All right, but here I'm going to get 0, 2, and 2h minus 3. Yeah, okay. All right, so, and then I'm just going to divide this row by 2 to make that a nice little 1 right there. Or actually, yeah, okay, never mind. So 1, negative 3h, 0, because this has an h in it, so I can't, I don't want to like mess with it anymore. 1, negative 5, 0, 1, and then 2h minus 3 over 2. All right, so the question is, I need there to be a solution, right? So I want values of y so that this is in the span of that. I want this matrix over here to have a solution. So for this matrix to have a solution, if I have 0, 1, negative 5, then this last one better be a repeat of that. This value right here better be a negative 5 so it can be an exact copy. I don't want it to be a different number than 5 because then I would get no solution, and I don't want that. So I want 2h minus 3 over 2 to be equal to 5. So multiply, get 2h minus 3 equals 10, so 13 over 2. Oh, wait a minute. 2h minus 3 over 2 to be negative 5. So it's negative 10. So actually that's going to be negative 7 over 2. Okay, all right, let's wrap it up here. Let A be this, B that, and W is all the set of linear combinations of A. So basically, when they say is B in W, well, B is all the possible linear combinations. So what they're asking you is B a linear combination of the vectors in A. So these things right here. So you just put it in there. You put 10, 3, 3. You put your matrix here, 2, 0, 6, negative 1, 8, 5, 1, negative 2, 1. You ref it. And when you ref it, this is what you get. You get 5, 1, 0, 1, 0, 3, 0, 1, 1, 0, 0, 0. And so you ask yourself, does this have a solution? Yes, it does. It's infinite solution. So your answer is yes, it is. All right? And don't worry about this one. Let's skip that one. Okay? All right, that's it. Sorry I went over a little bit, but I went as fast as I could. And that's it. I'll see you in class. Bye-bye.